Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tear, and today I'm starting a new series. This is part one of a series on complex numbers. And in this lecture, I'm going to define complex numbers and talk about some of their most basic properties. Anyway, let's begin. I thought I'd first start out by just showing you a Venn diagram of different number systems. So let's look at the inside one and go out. The most inner oval in this diagram, the most inner set shown here is what are called the counting numbers. Those are the first numbers everybody learns: one, two, three, four, five, so on. Just numbers you count with. But then gradually you learn more and more different types of numbers. The more math you learn. First, you learn about zero, and sometimes people call the set of counting numbers. Some people say counting numbers start with zero. That seems to be a convention that's catching on these days. But in the old days, they used to call those whole numbers. Those are just counting numbers with zero added. And it really took a long time for zero to catch on for some reason. The ancient Westerners, ancient Greeks and Romans never came up with zero. I think zero was invented. I don't know if it was independently, but I know it was invented in India. Eventually, it got to the Middle East, and eventually, I think by the late Middle Ages, it got accepted worldwide. But it took a while. But anyway, so that's the counting numbers, and then you learn about negative numbers as well, and that gives you what are called the integers. The integers are just all negative as well as positive numbers without any fractions. And then later you learn about fractions, or fractions are just known as natural numbers. I mean, not natural, rational numbers. And a rational number is just a ratio of two integers where the denominator is not zero because you can't divide by zero. And then beyond that, you have what are called real numbers, and those include irrational numbers as well as rational numbers. And for a long time, those weren't accepted either. It's not so obvious that there are irrational numbers, but there, you can prove that certain numbers, certain real numbers, are not rational, such as square roots, square roots of numbers that aren't perfect squares, like the square root of two. There was an ancient Greek named Hippasus who proved that the square root of two was irrational, but the legend is that they had him drowned at sea because the Greeks didn't accept the notion of irrational numbers. But then you also have things like pi and e, and it turns out that most real numbers are irrational. It turns out there are more irrational numbers than rational numbers, in kind of a set theory sense. Even though both sets are infinite, it turns out the size of the irrational numbers is a bigger infinity than the size of the rational numbers. So rational numbers are the rule as far as real irrational numbers, as far as real numbers go, are the rule rather than the exception. And then notice that there's one more circle beyond that. That's what we call the complex numbers. These are the ones I want to talk about today. And these include what are called imaginary numbers. Every complex number that's not real is called an imaginary number. And so that just try to, for now, just accept the fact that there's a bigger set of numbers than the real numbers that we're going to work with. So anyway, we still have to define what the complex numbers are. And the way we do that, we start with something called the imaginary unit, written as I. This is a number that's not a real number, and it's defined to be the square root of minus 1. There's actually two square roots of minus 1, and you can't really distinguish between I and its negative just from this definition, but one of those numbers is I. The other one turns out to be minus I. But anyway, this is the usual starting point for complex numbers. You assume that there's this unit called I that's equal to the square root of minus 1. You know that no real number squared could be minus 1 because the square of every real number has to be non-negative, positive unless it's 0. 0 is the only square of number whose square is equal to 0. But let's just for now accept that there's this number called I that has its properties and see where it takes us. So let's see what we can do with it first. Well, we can look at some small powers of I, And I to the 0th power, that we should set equal to 1 because every number to the 0th power is 1 by definition. Except for maybe 0 to the 0th power, which most people say is undefined. But every non-zero number, if you raise it to the 0th power, will give you 1. So why not have that hold for I as well? And then, of course, I to the 1st power, any number to the 1st power is just itself. It just means you're multiplying by itself 1 times, you're getting back itself. So I to the 1st power, I to the 1 is equal to I. What about I squared? Well, that's easy. We define I to be the square root of minus 1. So by definition of a square root, that means if we square it, we get back minus 1. So that wasn't a problem. And then you can get bigger powers just by using the distributive property. For instance, I cubed, that's the same as I times I squared. But since I squared is minus 1, that's going to give you minus 1 times I, or minus I. And what about I to the 4th power? That's pretty easy too. I to the 4th power is I squared quantity squared. You know that minus 1, that's going to be negative 1 quantity squared, and that's going to give you back plus 1. So by the time you calculate the 4th power I, you're back to 1. Notice that. And there's actually a kind of a pictorial way you can visualize these powers of I. You can think of them going around in the circle. And this thing is called the Argon diagram, by the way, or the complex plane. I'll get to that later. But if you imagine 1 and the complex plane is just the unit 1, a unit length of 1. So you're working in centimeters. It could be 1 centimeter to the right of the origin. And then if you look at I is just the number on the y-axis, 1 centimeter from the origin. And then if you take bigger powers of I said I squared was minus 1. So if you think of I as just like a 90-degree rotation, well, if you rotate another 90 degrees, you get 180 degrees, which is going to give you the number minus 1, which is the number 1 centimeter to the left of the origin. And if you look at minus I, that's going to be the number, again, you're rotating 90 degrees counterclockwise. That's going to give you a point 1 centimeter below the origin. And then, like I said, if you take the 4th power, you get back to 1. So, but there's no reason you have to stop at the 4th power. You can keep doing this as many times as you want. And you'll see that this pattern repeats. It repeats with a cycle of 4. That's why they call this the I cycle. And it's pretty easy to, with that in mind, it's pretty easy to calculate any power, any integer power of I, because you only have to take the exponent modulo 4. I mean, here's some bigger exponents. So since I to the 4th is 1, you keep going. I to the 5th is I to the 6th is minus 1, I to the 7th is minus I to the 8th is 1, so on. And if you wanted to calculate, say, I to the 2003, how would you do that? Well, that's pretty easy. You just take 2003 mod 4. You divide 2003 by 4 and see what the remainder gives you. The remainder is going to be 3. So I to the 2003 is the same as I cubed, I to the 3rd power, and that's going to give you minus I. So that's all you have to do if you want to count any integer power of I. And I haven't talked about complex numbers yet. I've been talking about I. But a complex number is really just any number that has a real part, which we call A, an imaginary part, which we call B times I, where A and B are both supposed to be real numbers. So B is another real number. And it turns out that if you just define the set of all numbers of this form, A plus BI, where A and B are real numbers, that gives you what's known as the set of complex numbers. So that's just a definition of the complex numbers. And then there's something important associated with complex numbers known as the Argon diagram. I don't think people use this name that much anymore. I think people prefer to call it the complex plane, but it was named after a early 19th century French mathematician named Argon. As far as I know, he was the first person that came up with this pictorial representation of the complex numbers. Uh, and the way you should think, I mean, they give you several examples on this slide. You can look at 3 plus 2i. These are just like points. Think of a complex number as a point on an Argon diagram, or a point on a complex plane, if you like. Those are all complex numbers, and that's all they are. You can even think of them as an ordered pair of real numbers if you like. I think a nicer way to think of them is as vectors. And I think this is a really nice picture right here. So we've got a complex number which we're calling z here. And z, like I said, every complex number has a real part and imaginary part. So we say z is the number a plus bi, where a is just some real number and b is some other real number. And that gives you what looks like a vector in the complex plane. And you probably learned when you were learning about vectors, two-dimensional vectors anyway, that there's two different ways you can represent a vector. One is what's called the Cartesian or rectangular representation. And that would be a plus bi. Or maybe if you wrote it as a vector, you wrote it as a comma b. Or maybe you call it ai plus bj. There's different ways you can represent vectors. But it's just a vector whose, the x coordinate, I guess if you say if you're working with vectors, is a. And the y coordinate is b. So that's just another way of saying the real component of z is a and the imaginary component is b, or the imaginary part is b times I. So, but that's just one way you can represent a complex number. And you probably learned of another way to represent a vector in two dimensions besides the rectangular representation. There's also something known as the polar representation. That's where you represent the vector in terms of its length or its norm, which we're calling r here. Uh, and by they don't actually give you a formula for r, but you can use the Pythagorean theorem. It's pretty easy. So if you look at this triangle here, this is a right triangle with legs. The horizontal leg has length a, and the vertical leg has length b. So by the Pythagorean theorem, r is just equal to the square root of a squared plus b squared. They don't show that, but that's true. So that's how you can get r in terms of a and b. And what about and it's not just enough to r. You also have to know the angle that this vector makes with respect to the x-axis or the real axis in this case. We're calling that angle theta. And there's another formula for theta. They don't give it here, but theta turns out to be the arctangent of b over a. You have to be a little bit careful because it depends on what quadrant you're in. That formula is really only holds if theta is less than 180 degrees, if you're in the first or second quadrant. If you're in the third or fourth quadrant, you have to take into account the sign of b, which is negative in this case. It has a negative imaginary component. And if that's the case, you have to add 180 degrees or pi radians if you like. But then they do give you the formulas for A and B in terms of R and theta. These are easier. So, I mean, since you just use simple trigonometry here, you've got this right triangle with hypotenuse of length R and angle, the angle that's not the right angle or the angle going from the x-axis to r is theta. So just from trigonometry, we know that a is our cosine theta and b is our sine theta. And if notice if we plug these values in for a and b, we get a very remarkable formula here. We get z equals r cosine theta plus I times r sine theta. That's a polar representation of a real number. I'm probably jumping the gun here, but there's actually another way you can write that. You can write z equals r e to the I theta, which is a really, really remarkable formula. That's due to Euler, who proved that e to the I theta, if you can imagine that, is equal to cosine theta plus I sine theta. But I'm jumping the gun here. I'll talk about that more in a future video. But anyway, just remember that these two representations of complex numbers, and both of those representations are very useful. And anyway, that concludes my first video on this series on complex numbers. I hope you enjoyed it, and thank you for watching, and long live math. And I'll see you next time. Bye.